How does a chloride current change the membrane potential? We address this question, of course, in physiological conditions. It means that we have a physiological concentration of chloride ions inside the pipette, so that we have a physiological concentration of chloride ions inside the neuron here, the postsynaptic neuron. And we record the changes of membrane potential, so we are in current clamp mode. We record the changes of membrane potential in response to GABA release. So we also block the glutamatergic synapses, and we record only the activity of these synapses, but in current clamp mode. And what we record is a small hyperpolarization of the membrane, as we saw in the first slides. This slight hyperpolarization of the membrane is due to the chloride current. Why? Because we are here with an equilibrium potential of chloride ions of minus 59 millivolts, nearly 60 millivolts. Due to concentration gradient, chloride ions have a tendency to enter the neuron. But due to the electrical gradient, chloride ions have a tendency to exit the neuron because they are attracted by the plus charges on the outer side of the membrane. The two forces are equivalent at ECL. So at minus 60 millivolt, there is no net flux of chloride ions, no current, no change of potential. Here we are at minus 50 millivolts. So what is going to happen? Chloride ions are going to enter and to hyperpolarize the membrane until the membrane gets to minus 60 millivolts. This is why sometimes there is a very small hyperpolarization, sometimes nothing, sometimes it's a small depolarization. So this response here is not always the same. It depends of where is the equilibrium potential of chloride ions. And it's not the same in all neurons of the brain. For example, we have neurons where the equilibrium potential is at minus 70 millivolts. Other neurons where it is at minus 60 millivolts, and other neurons where it is at minus 50 millivolts. So on the left here, when the equilibrium potential is at minus 70 millivolts. At 70 millivolts, of course, there is no current because we are at the equilibrium potential of chloride ions. Now, at minus 60 millivolts, we have a small hyperpolarization when GABA-A channels open because the membrane has a tendency to go to the equilibrium potential of chloride ions. And the hyperpolarization is larger and larger as we depolarize the membrane. In the middle, when the membrane is at minus 60 millivolts, there is no current. When the membrane is at minus 70 millivolts, then the current is reversed because the membrane has a tendency to go to minus 60 millivolts and you have a small depolarization. At minus 50, it's the contrary. We have a small hyperpolarization because the membrane has a tendency to go to the equilibrium potential of ECL, which is minus 60, and also an hyperpolarization, which is larger at minus 40 millivolts. And now when the reversal potential is around minus 50 millivolts, GABA has a depolarizing action at hyperpolarized potentials, more hyperpolarized than minus 50. At 50, it has no effect. And at 40 millivolts, it has a hyperpolarizing effect. So if we look, for example, at a membrane potential of, let's say, minus 60 millivolts, in some neurons, GABA will be hyperpolarizing. In some neurons, it will have no effect, no visible effect, because we will see that it has an effect, but we will see it later. And sometimes it has a depolarizing effect. So always remember that when you want to know what is the effect of GABA, you have to know where is the reversal potential of chloride ions and at which potential you are recording.